Hi, my name is Sid, and I'm a sophomore here at UNC. This past summer, I worked as an orientation leader, in which my students expressed to me that they were afraid of chemistry and thought it was really confusing. Even though I tried to reassure them and told them about how chemistry is my favorite subject, some of that fear stayed with them, which is why I really want to be a ULA. I want to teach students that asking why is very important. By asking why, they can break topics down into their smallest pieces and understand how they work together, and then make connections and across units and build confidence that will carry them throughout their course. I've seen this in my own personal experience doing research in the PILAC lab, and where I help study intrinsically disordered proteins. By constantly asking why and trying to question everything we do, I really understood the scientific process and started to get my feet underneath me. You know, and I really learned that being prepared to fail and ready to learn is the best way to be successful. As a ULA, I want to bring these concepts that I've learned into an environment in which students feel comfortable to express their questions, think out loud, and just build an understanding that will help them be successful in all the chemistry courses that they take. All right, for the reaction aqueous silver plus aqueous chlorine becomes solid silver chloride at 25 degrees Celsius, the change in entropy of this reaction is negative 570 joules per mole times Kelvin, and the change in enthalpy of this reaction is negative 250 kilojoules per mole, with a change in free energy of negative 80.1 kilojoules per mole. Is this reaction more entropically or enthalpically driven? So, this is a very packed question, but it gives us plenty of numbers to play with to see if this reaction is more entropically or enthalpically driven. So, as always, we should start with writing down with what we have and changing all the units to be the same, just so it's easier to visualize the numbers. So, I'm going to start with temperature, which is 25 degrees Celsius. Our change in entropy is negative 570 joules per mole times Kelvin. Our change in enthalpy is negative 250 kilojoules per mole. And our change in free energy is negative 80.1 kilojoules per mole as well. So first, let's get all the units the same. And so what I notice here is that delta H and delta G have the same units, but delta S, delta H, and delta G all have different joule values. And so I'm going to change delta S to kilojoules so it's easier to work with. And so I will do that by multiplying it by its conversion factor. So 1 kilojoule on top over 1,000 joules is equal to negative 0.570 kilojoules per mole times Kelvin. Looking up again, I also see that our temperature is in Celsius while our entropy is expressed in Kelvin, so I want to change that to Kelvin. So to do that, I simply add 273.15, which makes this new temperature 298.15 Kelvin. Now that we have that, we can play with all our numbers. But how do we exactly change them to see our answer? We need to use an equation. And this equation is delta G is equal to delta H minus T delta S. And so then I'm going to plug in our numbers and simplify it down, and we will be able to see our answer. So negative 80.1, I'm going to leave out our units just so it's easier to visualize, is equal to negative 250 minus 298.15 times negative 0.570. And I'm going to write this again, multiplying these two numbers right here, so it makes it even easier for us to visualize. And so now we have negative 80.1 is equal to negative 250 minus negative 169.9. And underneath it, I will make sure I write our variables so we remember what we're working with. And here we go. So now let's think about this. So for a delta G to be negative, that means that um, that means that this side over here also has to be negative. And what we can see here is that a negative and a negative become a positive, which means that delta H is a lot. Delta H has to drive this reaction because this number right here at the end will become positive. And so delta H drives the reaction. Conceptually, this also makes sense because this means that a change in entropy is negative, which kind of makes sense because when you look at the reaction up here, we have two things aqueous that become one thing solid. So the overall order of the system increases, which means there's a decrease in entropy. And from our equation, we know that if delta G has to equal to delta H minus T delta S, if entropy times temperature is a really large negative number, and both of these are positive, then it can overpower our enthalpy and then be the one that drives this reaction forward. But however, in our case, because our entropy decreases, but the delta G is still negative, that means that enthalpy drives this reaction.